Hello and welcome back. My name is Mike Price. We are talking today about section 1.2, the graph of a function. We are going to tackle the following learning objectives. In this video, we will endeavor to tackle all three of these. I know, really ambitious, right? So first one is to review the rectangular coordinate system. That really ought to be review. I'm hoping that you have some familiarity with that. I'm also hoping that you have graphed functions before, or at least graphed any sort of equations before. And then finally, we will study intersections of graph. We'll get a brief little taste of the vertical line test, and we'll look at intercepts of graphs. So the coordinate plane is basically made up of all of these points. We represent these points as coordinate pairs, ordered pairs like this. So our horizontal component is given by x, our vertical component is given by y. And although there's nothing special about those letters, they're probably the ones that you've seen, I'm guessing. In fact, I'd probably be willing to bet money that those are the ones you've seen. So this first component, x, is the distance to the right of this special point, the origin, and the distance up and down, the vertical distance, so above is considered positive and below is considered negative, from this origin is denoted by this distance y. So we call the origin 0, 0, and then anything else is either to the right or above or below and to the left of this point. Okay, so graph of a function, so we give the function a name and we want to see its graph. It's just a bunch of points. It's the points that consist of picking an input and then plugging that into whatever your function looks like, and then seeing what that output is. So the graph is just all of these points, and they generally form smooth curves because these points are infinitely close to one another. But they give you all those classic shapes you've seen, lines and waves. And then there are interesting graphs that are not graphs of functions, for instance, like circles. But we do this for every x that it makes sense to do it for. In other words, we do it for all the x in the domain of our function. So quick example just to get us in the ballpark, we've got f of x is x cubed plus 3 up here. And then a graph generated by Wolfram Alpha looks something like this. So just to note some key things about this, here's our y-axis, here's our x-axis, or horizontal axis and vertical axis. We've got our origin right here in the middle where these axes meet, the point 0, 0. And then just to pick a point out of there for fun to take a look at, maybe if we looked over here at x equals -1, it looks like it's supposed to have a y-coordinate of 0. And we could verify that in our equation. So if we take -1 and cube it, oh, I love drawing like a second grader. -1 cubed is still -1. And then we subtract. You have to be a little bit careful about signs here, but subtract -1. Subtract our input. So this is -1 plus 1. So that actually is 0 as predicted. So our graph isn't totally off. We're at a height of 0 there, which is what this graph seems to be predicting. A couple of other points. So this graph does pass through the origin. That's not required of any particular graph, but f of 0 actually is 0, so we do pass right through that special point there in the middle. And then just for additional flavor, we've got one additional point to look at. If we plugged in a half to our function, we should get -3/8 out. I'd encourage you to verify that. And here's an x value of about a half. And if we follow that down to our function, somewhere in there is where this graph is predicting an output. And if we look at our horizontal values, it seems at least vaguely convincing that that could be at -3/8. Negative output because it's below the horizontal axis. So that corresponds to this point, 1/2 comma -3/8. So intercepts are places where the graph crosses either the horizontal axis or the vertical axis. I think a more responsible way to phrase this is horizontal intercept and vertical intercept, because again, there's nothing special about x and y. But I'm pretty sure you're familiar with using these letters, so I don't think there's any harm in it. So x-intercept is where we cross the horizontal axis, the x-axis. Y-intercept is where we cross the y-axis, the vertical axis. And here's a graph of something interesting here, kind of wavy, squiggly thing. And we can see its intercepts here. So x-intercept, for instance, is down here where it crosses at an x value of 1. Our y-intercepts are, there's actually 2 of them, up here at 1 and down at -1. So another thing that this illustrates is that what we have is actually not the graph of a function. So the way we can verify that is if we pick some vertical line, perfectly vertical line just like that, we can see that it touches the graph in more than one place. So why would that be a problem? Well, if you pick 0.5 as your input, if you have a function, there should only be one output for that. This doesn't have exactly one output. It's got an output up here at, I'm going to guess 0.9 something, and then an output down here at also 0.9 something. That's not okay. If you pick a particular input, a function should only give you one output. So this green line by itself is enough to say that whatever generated this curve was not y as a function of x. So that's called the vertical line test. So let's try to graph a function given a formula. So we've got f of x. Again, we're sticking to the tried and true, just naming it f for, I guess, lack of creativity. So f of x is square root of quantity 3 minus x. Our job is to sketch its graph and identify intercepts. So one tried and true way to get a graph is to plot some points. And if you have no inspiration, then you could just try plotting things around 0. Whole number values, integer values like -2, -1, etc. work pretty well. I picked -1 in particular because if you note, this is going to go pretty well when we take 3 and we subtract -1. This is going to give us something nice under the radicand. Because if we have 4, square root of 4 is actually pretty good. Well, they're all great numbers. I don't mean to place judgment on them, but it is a whole number. Square root of 3 is fantastic. So if we plug in 0, we get 3 minus 0, square root of 3, good. We plug in 2, we get square root of 1, which is 1. We plug in 3, we get 0, because square root of 0 is still fine. Square root of 0 is 0. However, when we get to 4, 3 minus 4, okay, well, square root of -1. Again, not trying to place any judgment on these, but square root of -1 is not real. So we are trying to deal with just real numbers here, and so we put this little note here, it's non-real. You could say undefined, but it's you know, by a technicality, that's not really true. We do have ways of talking about these things as in terms of imaginary numbers, but we're interested in the real numbers here. So we could predict that the largest x value at which we're actually going to have any graph of this function is at x equals 3. Because as soon as we pass 3, we're going to get numbers that will create non-real outputs. So then our job is to connect these points, basically. Put them on a coordinate plane and try to draw a curve that connects them nicely. So this is Wolfram Alpha doing our job for us, but if we plot the points at 3 and at 2, at 0, and up here at -1, we should have all of the key points. It gives us kind of a basic idea, and then we can smooth it out in between. We're going to be using graphing calculators in our class anyway, so this won't be a huge issue, but it is nice to know how some of these things would get generated. And then we should be able to notice that we have intercepts from our graph. It looks like it's about 1.7 for the vertical intercept, and at 3, 0 for our x-intercept. And just glancing back at our table of values, we kind of got lucky here. We plugged in 0 for x. That's a surefire way to get the vertical intercept. If you plug in 0 for x, you will get the y-intercept. And then it's slightly more complicated, but we wanted to get 0 for an output. 3 is what gives us a 0 for an output of this function. So those are our, respectively, y-intercept and x-intercept for our graph. Next time, we'll come back and talk about our final learning objective for section 1.2. Thank you.